Hello everybody. So what you're going to be doing today is figuring out a way to calculate truss deflections. So imagine you have a simple like a beam or anything. So if this my pen is my beam, so you know how to calculate the deflection if I apply a load in this direction. So essentially this is going to bend, or if I have a ruler like so, if I apply a force here, basically this is going to bend like in a curve. So you can actually use the equations of beam deflection, and then you should be able to figure out what the deflection is. Same way, if I have like a linear scale or a linear wire or beam, and then I apply a force basically in this direction, kind of like pull it down, or if I compress it, push it up, what you can basically do is use the stress strain relation, where you would calculate the stress in the particular section. So basically you take this, calculate the force divided by the cross-section area, which will give you the stress, and then you can use the Young's modulus, and then you'll get the strain, and then use that to actually calculate the deformation. Unfortunately, so what you're going to do is, like when you have a truss, you'll notice that this is no longer the case and things get a little bit more difficult. So that's why we go here. So imagine you have a truss, so you have this point here where I apply a 100 Newton load, and then what happens is I'm going to build the truss here. So this single beam is not enough, so I add a couple of more. So what that means is this point here is kind of like a fixed support, which prevents this joint from moving either up or down. And then this point here, this can potentially allow the link to move either up or down like this, and then it's locked basically in the other direction. So what we can potentially do is we can basically resolve the force of the diagonal link along the vertical and the horizontal direction, and then you should be able to calculate the equilibrium calculation. So we should be doing that shortly, but just to give an idea of the force magnitude, we can do this. And then once we do that, it's reasonably clear that the links marked in red are going to be in tension, and the links marked in blue are going to be in compression. So as you've probably imagined, the red link is going to become longer and the blue link is going to be shorter. And then since the connectivity still needs to be maintained, the structure is going to deform a little bit. So you'll notice that the final structure looks something like this. Obviously, if you can calculate the expansion and contraction, you can potentially use the geometry and then solve for the final position of the 100 Newton force. Unfortunately, this is not always that easy. So let's look at the learning outcome. So the learning outcomes are going to be to solve the truss displacement. Basically, we'll also apply the method of joints to determine the internal forces. We'll also recall the concept of virtual work, and then we'll use this method of virtual work to solve for the real truss deflection. So this is the problem statement. So what we're going to do is we're going to try to calculate the truss given below. So we want to figure out the displacement along a 45-degree line. So the external force is 100 Newton, and then we have these two links 1 meter long each, and then the material is aluminum, 70 gigapascal. We're going to assume each of this cross section 10 millimeters. So since 45 degree is a little bit more tricky, so what you're going to do for a displacement calculation is to kind of like reframe this. So what you're going to say is, okay, I'm going to solve it along the horizontal and the vertical direction. So we're going to try to calculate the displacement, and then we can calculate the displacement along the 45-degree line by taking the cosine and the sine. So this angle here would be 45 degree in this case. So let's see if you're clever enough to actually solve for the horizontal and the vertical displacement of this joint 1 here. So what we're going to do is, if you wanted to calculate the displacement, we first need to calculate the internal forces in the link. So this can be done in method of joints. So why don't you actually solve it right now? Okay, so the first thing we're going to do is look for equilibrium of the different joints. So we'll start basically with joint number 1. So if we just isolate joint number 1, so we see that 100 Newton force, and then because we're going to assume that the internal forces are going to be tensile, this link 1, 2, if you replace it by a tensile force, it's going to be a force from 1 towards 2 here, and then 1, 3 becomes a force to the left at the same point. Once we have this, we can basically solve for the x equilibrium, which basically is T13 minus T12 cos theta equal to 0. Theta here would be 45 degree because of the geometry. Similarly, we can use the y equilibrium, and then this is the equation we get, and then we can actually solve for T12 and T13. So we get T12 is 100 square root of 2 and T13 is minus 100 newtons. So we can extend this and then solve for the equilibrium of joint 2 and 3. So if you look at equilibrium for joint 2, we notice that once again T12, because it's along this direction, assumed to be tensile, points towards the joint number 1. T23, again, if it's assumed to be tensile, points in the downward direction. So we can solve. We find T23 is minus 100. Once again, when we get a negative sign, that basically means that the initial tensile force is wrong. So you don't really have to recalculate these values. You can kind of like quickly infer that the actual force is going to be compressive in nature. So here, each of the link that we have is going to be like my pen I have here. Each of it is either going to be tensile, which is kind of like pulling here, or compressive, which is going to be, maybe this is, it's going to be compressive where it's like pushing towards the center. So what we can do is like basically take the cross-section area here. So this is going to be A. So this force, whatever we have here, divided by the A would give you the internal stresses. And then you can use the Young's modulus and then really quickly calculate the strain. And then using the strain, you can actually calculate the deflection. So the actual formula would look something like this. My stress is going to be the load divided by the area, and then once we have the stress, you can calculate strain would be my stress divided by the Young's modulus, and then once I have the strain, my change in length is going to be strain times the length of that particular beam. So here you can basically replace for each 1, 2, 1, 2, 1, 3 and 2, 3, you can basically do the same set of calculation and then calculate the internal displacement or deformations in the link. So once we do that, we find that T12 will be 100 root 2, T13 and T23 will both be negative 100. So this we're going to be denoting, so using these values, you can calculate the displacement delta L12 would be 100 root 2 times root 2 by AE. Similarly, you can calculate the other ones, 1, 3 and 2, 3. Okay. So now we are actually interested in calculating the displacement of point number 1. Let's see if we can figure this out. So it's fairly obvious that delta y2, which is basically this point here. So because this point 2, 3 is fixed, so if this link becomes shorter, you'll notice that 2 moves down. So my delta y2 would be equal to L23, which is basically going to be equal to minus 100 divided by AE. If you look at 1, 3 here, this link, if this gets shorter, you will notice this can potentially also rotate here. But if we ignore the secondary effects of the rotation, we can conclude that the delta x1, how far this guy moves, is going to be almost equal to delta 13, which will be equal to minus 100 over AE. Unfortunately, delta y1 is not as easy to calculate. So if we consider just the 1, 3, so how does it come about? So this is going to be the rotation of 1, 3. So essentially this link goes from here. This can potentially rotate like so. So that is going to be causing some displacement here. but then you will notice that this is not that great because the value of the actual rotation is unknown. So what is the other thing we can do? So if you can think of y1 also comes from the expansion or the change in length and the rotation of link 1, 2, and then this is again still unknown, but we can potentially calculate this. So let's just look at the link 1, 2 now. So we're going to assume link 1, 2 would rotate basically by an angle of theta 1, 2, but then we'll notice that the end point 2 itself also would have gone down a little bit, and then from there this is going to be rotating. So if you assume 1, 2 is going down by some value of delta y2 that we previously calculated, and then from this point on you're going to have an expansion and then a rotation of this link. So our final link is going to be in red as shown here, where this dotted line here is going to be delta 1, 2, and then this one we're going to approximately assume is almost equal to L12 times delta theta 1, 2. So this is valid when the displacement and the theta are very, very small, where this actually just affects as a rotation. So once we have that, if you just consider just the two displacements, let's see what happens. So this is my x and the y axis, and then let's bring it closer to here, and then let's rotate our particular shape. So now it's the same shape, but we've rotated so that I'm looking at the delta L12 and then the radial and the tangential direction of the link. So notice that my delta x1 in this particular equation is going to be delta L12 cos 45. So here the angle is 45 degrees, and then we have L12 delta theta sine 45, and then because we have the y2 added, the whatever y we get is actually going to be delta y1 minus y2 would be minus L12 sine 45 minus L12 delta theta 12 cos 45 degrees. So the L12 delta theta, this term is unknown. I don't really want to solve it, so that's the reason it's a little bit smaller. And then notice that I'll try to eliminate these two. In this case, sine 45 is equal to 1 over root 2, cos 45 equal to 1 over root 2. So these two terms are actually identically equal. So once I do that, I can actually write delta y1 in terms of delta y2, which I know, delta x2, which I also calculated, delta L12, which we calculated as the internal stress, internal strain, or internal displacement. So that basically means everything in this term is actually known, so I can substitute these values in. I will notice that delta y1 is given by this formula, and then I can calculate delta y1 is minus 428.84 divided by AE. So A is again the cross section, E is the Young's modulus, and the units, if I use an SI units, will be in meters. If I wanted to calculate delta 45 degrees, so recall, I'm going to basically recall from the previous slide. So I can basically calculate it as delta x1 cos 45 plus delta y1 sine 45. If I do that, I'll actually notice that the delta 45 is actually equal to 412.1 AE. So it'll actually have a negative sign based on the direction in which you're looking at. So then the question is there an easier method? Unfortunately, the answer is no. So we're actually going to use the method of virtual work, which again uses different set of equations, but it's not like significantly easier that you can do a back of the envelope calculation. So before we do that, let's recall some of the concepts in virtual work. So when a structure is in equilibrium, the net virtual work done is 0. So this is true either for the virtual or the real work. Alternately, we can say when a structure is in equilibrium, the net external virtual work should be equal to the net internal virtual work. So what we do is, if we wanted to calculate a force along a particular direction, we would apply a virtual displacement. If we wanted to calculate a displacement along a particular direction, we'll apply a virtual force. Since we want to actually calculate the displacement along a 45-degree line, we're going to apply a virtual force along the 45-degree line. So we assume that the virtual force produces internal virtual forces for equilibrium, and the internal and external virtual forces do not cause any additional deflection or deformation. The external virtual force and the corresponding internal virtual force is assumed to be present from the very beginning, or kind of like the beginning of time. Just for simplicity, we are going to assume that the virtual force is 1 Newton. Now we imagine that the external real force is added, resulting in internal forces resulting in internal deformation. So now J1 actually moves along the direction of the virtual force, which results in a external virtual work. So there's going to be a real deformation times the virtual force will be equal to the external virtual work. Now, since our internal virtual forces are present kind of like from the beginning of time, what happens is when each of the link actually deforms due to real deformation, the product of the real deformation and the internal virtual force results in internal virtual work. Since the structure is in equilibrium, we're going to equate these two terms. Basically the external virtual work and the internal virtual work, and then we can solve for the displacement, because the only thing that's going to be unknown is the real external deformation. So basically the real external deformation here is the only thing that's unknown in this equation. So let's see how this is done in practice. So what we're going to do is ignore the virtual force and calculate the real internal loads Te sub I due to the real external force P. So then we can calculate the deflection or the deformation using this formula over here. Once that happens, we're going to apply just the virtual force and ignore the real force, and then calculate the internal virtual forces T sub Vi due to the virtual force PV, which is 1 Newton, and then this is going to be along the direction in which we want to find the deformation. Again, these two would be done, both of these can be done either in method of joints or method of sections. Once you do both of these, what we're going to do is calculate the internal virtual work, which is going to be the sum of these two products, which basically becomes this equation over here. If AE is constant, we can basically pull this out of the summation, so this kind of becomes outside. And then equating the internal virtual work to the external virtual work, we find that the displacement along the virtual 1 Newton force would be 1 Newton, the virtual work divided by 1 Newton, which basically is this formula over here. So to make life a little bit easier, we can actually create a table. Before we do that, we have to actually calculate the internal virtual forces. So assume this 1 Newton is applied here at a 45-degree angle, and then calculate all of the internal forces resulting from this external virtual 1 Newton force. So again, we're going to use the method of joints. So we can look at equilibrium of joint number 1, write the equilibrium for the x direction, write the equilibrium for the y direction, and then once we do that, we can solve. We find that T12 is -1, T13 is square root of 2, and then we can write the equilibrium for joint 2, and then we'll find that T23 is 1 over root 2. So right now we basically have everything that we need, and then we can basically fill in our tables. So the easiest way to do this is to have a table with the length, the internal forces, the internal deformation, the virtual forces, and the work done. So I'll give you the lengths here, not too shabby. We already calculated all of these values, so we're going to fill in the forces here. Now I'll give you a few minutes to actually fill in the deformations. So these are the deformations. Make sure we have the correct signs. These are real deformations inside the link. Fill in the virtual forces. Once we have that, we're going to multiply these two, and then like basically this would be the real deformation inside times the internal virtual virtual force. Product of these two will give like each segment work done in each link. So we can fill that in. So once we do that, we can calculate the total virtual work, which is going to basically be the summation of all of these, which we get it to -412.13 MSE312 divided by AE, and then we can actually use this to calculate the real deformation. Notice that when we compare this to the other method we used, we get the same value. So when you substitute in the values for AE, we'll notice that the displacement actually comes to minus 58.88 micrometer. So this is actually really small deformation along the direction of the force. So you'll also notice that if you calculated the individual deformations, they would have also been in the order of few microns. In summary, what we did was we calculated the truss deflection using kind of like a regular method, and then we examined why we needed virtual work, and then we examined how we can calculate real internal forces and real internal deflections, calculate the virtual internal force, and then we calculated the deflection using the method of virtual work. This method can be extended to calculating the deformation along any direction. So this basically concludes our video. Thank you.